that I'm going to give is actually in the chapter 2 of my thesis, which can be, Googled and can be found out. But I'll also, after giving the main part of the talk, I will also mention about other stuff, which can be found in other papers or in another chapter of my thesis. It was also my pleasure to see Nils after a while. And I've looked at the schedule and there were 2 talks about TQFTs. So this talk would also fit, fit into the schedule well. So let's start. Okay, you may be interested in this talk for at least 3 reasons. You could be interested in this talk if you are a topologist that you want to classify manifolds under the equivalence class of diffeomorphisms. So say you want to find a way to understand whether this manifold is diffeomorphic to this manifold. Of course, by not looking at it, because when you look at it, you see what's the difference, but trying to understand the difference by some local rules. And in physics, in condensed matter or high energy physics, one of the main problems is to classify quantum phases of matter, where you can formulate the problem as follows. You are given 2 Hamiltonians, say H1 and H2, and you try to understand whether the physical observables that you will get, the behavior of the physical observables that you get from this Hamiltonian system, whether this is the same as the physical phenomena that you would get from the second Hamiltonian system. What you would do is that you basically try to find the path from this Hamiltonian to this Hamiltonian and see whether things change drastically on the way. And maybe, sometimes there's no path between this Hamiltonian and this Hamiltonian, H1 and H2. So there are a lot of Hamiltonians on the way. There are a lot of H1 primes that you can reach from H1. There are a lot of H2 primes that you can reach from H2 without any drastic change, but these paths never cross. And in that case, we say this system is in a different topological phase or in a different quantum phase than this system. And the ultimate goal is to find out every possible phase and try to understand every possible physical phenomena that we can get from these microscopic models. And the third motivation comes from quantum information / quantum computing. The ultimate goal in that area is to engineer a quantum computing device that works with quantum mechanical principles and which are advantages in solving some of the problems. But for that machine to operate reliably, you would need first a quantum memory that is basically a physical system that is robust to local noise. In classical computers, this has already been achieved. But in quantum, the reason that quantum computer does not exist yet is basically this. So these 3 subjects have been beautifully unified in a work by Alexei Kitaev before 2000. And what we will see is a work that tries to understand this in higher dimensions and in principle in any dimension, but only the quantum memory part. So we are not going to deal with how to do quantum operations. Okay, well, let's just continue before I decohere. Okay. We have a loaded outline here, and this is a talk with more than enough messages. So bear with me, but if you are lost, please don't hesitate to ask questions. And otherwise, I'll try to explain things as much as I can. Since it's, I guess, supposed to be an introductory talk, I will give more motivations about this quantum matter and quantum error correction part. And then I will introduce basics about tensor networks and TQFTs, in particular state-sum TQFTs, which has already been done by Niels and Ekin on Friday. So this will be really brief and will be not nearly as clear as what they did. And then we will see how tensor networks or how TQFTs, in particular these state-sum TQFTs, can naturally be seen in the framework of tensor networks. And then I will claim that there is a more general tensor network framework, which in principle includes the TQFTs, and it in principle includes more than that, but that is still not known. And I will have the slogan that basically says that TQFTs are RG fixed points, and the general tensor network framework, you can have models which are away from RG fixed points. And we will see some examples if we have time. These are called Dijkgraaf-Witten models, which also appeared in Niels' talk, in talk by Niels. Levin-Wen models, which are some kind of generalization of what Kitaev already did. And then in 3+1 dimension, there's a model that's found recently by Walker and Wang. And all of these are TQFTs. So by construction and by the results, they are a special case of tensor networks. But I want to give the specific tensors that gives us the relevant states and operators of the topological ordered model. And at the end, I will pose some open problems. And this is actually an old talk that I gave, I guess, 3 years ago in the summer in the Perimeter Institute. And since then, there has been some developments in these open problems. But as far as I can tell, they are still widely open, especially some of them. But there are some nice work that appeared in the past 3 years. Okay. So let's start with the opening up these motivations a little bit more. So as I said, classification of phases has been a main theme in physics. And in thermal physics or classical thermal physics, we know that we have three phases, which are labeled as solids, liquids, gas, etc. And in quantum phases at 0 temperature, people worked out examples that has local order parameters. And these phenomena can be explained by Landau's spontaneous symmetry breaking. But when we came to 1980s, new kind of systems have been found where, these systems looked nothing different than any other particular system, except if you look at their boundaries, there are actually special or unusual things going on. And these are related to non-local order parameters. I guess the quantum Hall systems are the first examples of these. And people later defined something called topological order. So here this topological comes in principle from these non-local order parameters. But due to these non-local order parameters, these systems give us some properties, which depends on the topology of the manifold that we put on. So if we put these systems on a sphere or on a torus, there are certain things such as the ground state degeneracy and so on that are different, even though the Hamiltonian is the same. But for a while, people looked at these specific physical systems and found out these different kind of orders. But I would say, you know, with the advancements in quantum information and quantum computing, people developed a computational, you know, in-code computational approach for the classification of quantum matter problem. And this problem goes as follows. So we are interested in a many-body system that's put on a lattice, and we assume that we are given a gapped local Hamiltonian. What does that mean? It means that at every point, at every vertex of the lattice, we have a spin system of dimension d, and quantum states in principle lives in CD tensor n, assuming that we have n of these particles. We have big N of these particles or spins. So this is a huge Hilbert space. And then we define a Hamiltonian that acts in a local way, which means that it is a sum of Hamiltonian terms hi, where I denotes a local region. So this small hi acts non-trivially only on the spins that is in region I. And it acts trivially as an identity in all other regions. And by gapped, we mean that when you increase the system size n, the energy difference between the first excited state and the ground state does not decrease to 0. So it's kind of stops somewhere. So there's a non-zero difference between these two energies. This is basically what people like to call mass gap. That leads to exponential decay of correlations. But let's just, let's not go in there. So when we want to classify things, whatever they are, right, we need an equivalence relation, which I will come to in the next slide. But let me first define what we want to call trivial phase. A trivial phase is something that we want to label by a product state. So a trivial phase is what we call in quantum information is something that you can label by a state that has no entanglement at all. So this, this at every point, say we have a phi, and there's no entanglement between any point. The reason that this is a trivial phase is that you can actually find a Hamiltonian such that this state is the ground state of this local Hamiltonian. And this is a rather simple Hamiltonian because it does not involve any more than one spin. And this hi commutes with any other hj because they just don't touch each other. As you see, this hi is only defined for site I. It's acting on site I non-trivially and only on site I. Okay, what is the equivalence relation, right? How do we say that phase, this theory A is in the same as in theory B? There is a physical definition for that. If you can deform this theory A to theory B without closing the gap, when you don't close the gap, then you say that you are in the same phase. This definition gets mapped to the following definition in the language of quantum circuits or quantum computing. We say that the Hamiltonian H is in the same phase in Hamiltonian H prime if and only if this H prime can be mapped to H or vice versa by a local quantum circuit U log. Where this circuit has to be constant depth, which means that it does not scale with the system size. That is related to the fact that you don't close the gap, you don't close the physical gap. And this gets mapped to the states in a trivial way. And we will see that in tensor network approach, we can actually phrase everything in terms of states and can somehow bypass the formulation in terms of Hamiltonian, which is in principle much more easier, right? Because Hamiltonian includes every information, including every state. But if we can pose everything in terms of the ground state, then that is in principle much more easier.
So, anyway, Burak, can I ask a question? I would like to ask a question. Thanks. Sorry for interrupting, but so without closing the gap, what do you mean by that? Can I shrink the gap but not touch it to the?
You can shrink the gap on the way, but when n goes to infinity, of course, when n is finite, there is always going to be some kind of gap.
Yes.
But the problem is really about the thermodynamic limit. You should have many samples of this system for different system sizes.
Okay.
And you try to deform your Hamiltonian. Deforming Hamiltonian means that you perturb your Hamiltonian.
Yeah.
And you try to reach from one Hamiltonian to another Hamiltonian. And on the way, and when n goes to infinity, you want to make sure that this does not close, which means that there is always a non-zero difference in the energy of this state and this state.
Okay, thank you.
Yeah. So this already breaks our theory space into phases or equivalence classes, which we call phase or a quantum phase. This phase diagram enriches when a symmetry is added. I'm not going to open up this more, but yeah. Okay, so what about quantum error correction, right? Like, what's the relation of all these things, all this, in principle, physical objects or physical theories that, or physical studies that has been done, how can it be related to something like error correction, which is in principle nothing but engineering? Well, I would argue otherwise. I would say that error correction is actually fundamental because things that are persistent to imperfections such as noise, they must be robust or correctable against all these effects in some way. So if you look at things in that way, you say that, well, we are local, so noise in principle does not need to be local. So something can just come and smash everything, and in principle disorganize everything. But fortunately, the noise that we are considering and we also find in the nature is also local. I'm not gonna
a possibility for helping with the quantum error correction.
Excuse me?
Would machine learning be a good option or possibility for quantum error correction? I'm taking from the talk from before.
Machine learning will, in principle, help with everything, but it's a challenging problem. So we still don't know how to make use of that for quantum error correction. We can talk more about that, maybe at the end of the talk if we have time, or offline somehow.
Thank you. Thank you.
Yeah. Thanks a lot for the question. Yeah. So some examples of error correcting codes are languages. Our languages are robust to imperfections. I make a typo, you can still read it, you can still understand it. That is nothing but that, our words are encoded in such a way that they are reconstructible if we do some mistakes. The hard disks of our computers are error correcting codes. And there are some quantum hard disks that have been proposed theoretically, but still it's a formidable task as of today, and that's kind of a big open problem. What is the relation of all these to topological order or gap phases of matter? Well, this is the groundbreaking contribution of Kitaev. It's kind of, it's an at least $3 million idea that he recently got a prize for this. Basically, the idea is that the code space is the ground state space of a local Hamiltonian, of a particular local Hamiltonian. And the robustness comes from the fact that this ground state space is protected against local noise. Plus, it comes as a bonus, it is also protected against Hamiltonian perturbations. Here's this famous example. It's called toric code. Again, I don't want to go into the details, but what Kitaev did is that he came up with a Hamiltonian which acts on these spins on the lattice. He put the spins on the edges, but it doesn't really matter that much. He defined a local Hamiltonian in such a way that when you put this system on a torus, it has ground states degeneracy. So it has more than one ground state. And in particular, it has 4 ground states for this particular model. And the main feature of these ground states are that they are locally indistinguishable. So if I give you one of these states and I don't tell you which state I gave you, and I only allow you to do local measurements, I only allow you to do measurements on a disk, then you are not able to figure out which ground state I gave you because they all locally look the same, meaning that their reduced density metrics on a disk are all the same. And this is basically, from this property, you can get, or you can infer robustness against local noise, simply because if they look locally the same, local noise is not able to do anything to, to change you from one state to another state, which would disrupt the information that you stored. Okay, so given all these backgrounds, we are trying to understand all possible known systems like this, which can be understood in terms of spacetime TQFTs. We want to understand them in another framework, which is tensor networks. So let's go over the basics of these two things very quickly as well. So there are various tensor network states. One of them is called matrix product states. This is used to describe quantum states, quantum many-body states of n particles or n spins in a particular way. So as we said, this state lives in a really big Hilbert space. But most of these states, most of the states that lives in CD tensor n is actually highly entangled. And it turns out that physically or physically relevant states, which are low energy states of, say, gapped local Hamiltonians, they have been proven to have not that much entanglement. So we don't really use a lot of data to describe this ground state, but instead we can use a simple local tensor like this, AI alpha beta. So these I alpha and beta, they are labels, they're spin labels. And this one is what we call a physical spin label, and these are virtual spin labels. And the whole state, in many physical cases, for many physical ground states, it can be expressed in this way, where it is the linear superposition of these basis states from I1 to IN, and the coefficient in the linear superposition is given by a multiplication of these matrices. Like if you fix I1, I2 up to IN in this tensor, this number, AI alpha beta, it's a complex number. Now alpha and beta are the indices of a matrix. It becomes a matrix multiplication. So in this way, some of the states, which is called matrix product states, can be expressed only by the single tensor. So every information about this state is somehow encoded in this local tensor. Of course, it's a question that, how this local tensor can lead to, or how can we infer global properties about this state just from this local tensor? That's a viable and difficult question. And in some cases, as we will see in the talk, we will be able to understand that. And this is schematically shown in this way. When there are open legs, they are basically now physical states. And when the legs are contracted, that is basically tensor contraction. You can generalize this, just straightforwardly to higher dimension. Instead of using a 3-leg tensor, for example, you can use a 5-leg tensor, one of them a physical leg with 4 virtual legs, and you can construct tensor network states in higher dimensional lattices. And you can even try to understand renormalization by these tensor network states. So in principle, you can in principle explain or formulate everything in terms of tensor networks, but the problem does not get easier just because you draw pictures. And the whole area of tensor networks is about basically what I said, how to extract global information about these states from these local tensors. And they are also useful numerically because the lack of entanglements in these states, or the amount of entanglements, gives us a leverage to do numerical calculations in a much easier way. Okay. I'm not sure I should do that, but let's go over this quickly. Another way to construct tensor networks is to construct them from non-entangled states. So let's start with a collection of states where we have only bipartite entanglement between nearest neighbor sites. So this line supposedly mean that there is a spin here on this end, and there is another spin on this end, and this is a maximally entangled state. And as we said, as we saw at the beginning of the talk, this is what we would associate with a trivial phase. Because this state, which is just a tensor product of these bipartite maximally entangled states, it has a natural Hamiltonian such that it's the ground state of that. So this H prime, which is given by the sum of these projectors, has many states above the ground state, but it only has this state as its ground state. And there is a gap, which is basically 1. So to make things more interesting, we apply these linear maps A on this state omega tensor 2n. So at each side, at the intersection of these 4 legs on this side, we apply this linear map A, and we obtain these physical degrees of freedoms. This is why I call these contracted legs as virtual degree of freedom, and this as a physical degree of freedom. And this, in principle, this gives a many-body state of n spins. And in some particular cases, when this A satisfies some conditions, we can show that there is a Hamiltonian H such that psi is the unique ground state. And in topologically ordered systems, it's going to be something more exciting than that. There will be more states which will be the ground state of this H. So there will be ground state degeneracy, and all these states will look locally the same, and they will be connected to each other by non-local operators. Okay, so I will show these tensor network states in this way, and sometimes in the dual picture by using triangulations, but this is basically what a tensor network state is, or how it is constructed in the most general way. So as a summary, in these tensor network states, there are virtual and physical Hilbert spaces, the contracted legs and the uncontracted legs. So as I said many times, the structure of the whole state is somehow encoded in this local tensor A. So what we do is that we go from the local tensor to the global state, and from the global state to the local Hamiltonian. This is somewhat unconventional from what is taught in the schools, because in the schools we are given a Hamiltonian, for example, a hydrogen atom Hamiltonian, and we try to find the states. So we go from the Hamiltonian to the states, but in many cases this is a really hard problem. So instead of doing that numerically or analytically, it is much easier, and in some problems it is actually it gives you a benefit to first make an ansatz by, say, using these local tensors and try to understand the properties of these. And if you're lucky, or if your methods allow, you can actually derive the local Hamiltonian from that, such that this state is the ground state of that.
Can I ask something as well? Again.
Yes.
So in this pedagogical summary, so you're given a physical system and you're trying to probe it with local tensors, but the problem is now finding the right local tensors such that you find the correct Hamiltonian. Is this now the case?
So we are not really probing the state. We are not really given a state. To be more precise, we are actually given this tensor A, that maps, that is a linear map from this 4 Hilbert space, to this one physical Hilbert space, local Hilbert space. And from this local tensor, we construct a global state psi, which is this.
Who gave us the A?
Oh,
we tried to find it like by an educated guess, right?
No. Yeah, that's great. Great question. A can be an educated guess. And the whole problem is to find the right A for a relevant Hamiltonian, right?
Okay, yeah.
Well, of course, we don't really know how to do it in principle. And numerically, you can approach this problem numerically by assigning a random A and try to minimize the expectation value of your Hamiltonian to find the ground state.
Okay, all right.
So this goes a little bit also in the way of machine learning, but not necessarily. And in some cases, you can also make educated guesses, as we indeed did back in 2014 for topological ordered models. And you basically get the whole answer suddenly.
Okay, thank you very much.
Burak, you have lost 5 minutes, by the way, but you can go a bit further.
Okay, let me just be quick. Thanks a lot for the warning. You can also express Euclidean path integrals in terms of tensor networks, but let's skip this part. So what we're going to do is that we express the ground states of many-body lattice systems as tensor network states. And the goal is that we will try to find the conditions on these local tensors, and we are seeking for if and only conditions, if it ever possible, such that the tensor network state satisfies the required physical properties. And in the case of topological ordered tensor network states, we will axiomatize the conditions that should be satisfied by these local tensors, such that we get the topological order in the global state. And one of the results is that TQFTs or state-sum TQFTs appears as fixed points of this tensor network formalism. Let's go over TQFT really quickly, and also because Niels and Ekin already did it. So an n+1 dimensional TQFT, the goal there is to understand whether two manifolds M and N, whether they're similar to each other or diffeomorphic to each other. And we want to find a number, a way of assigning number to these manifolds in such a way that, if the manifolds are not diffeomorphic, these numbers are not equal to each other, and vice versa. So the problem in what way? Okay, yeah, going from left to right is not easy, but going from right to left can be done. So we can do the following. We can say that, if M and N are equivalent to each other, we can come up with a scheme where these numbers are the same. But these numbers being the same, they do not always imply M is equivalent to N. So it may be our lack of imagination or the lack of the power of our method, such that even though these numbers are the same, the manifolds are different. But we will, it is what it is, and we will try we try our best. Okay, how do we do that? In the case of state-sum TQFTs, we triangulate the manifold M, which means that we express it in terms of n+1 simplices, and we glue them to construct the manifold M. We put degrees of freedoms on 0, 1 up to n simplices. We assign a tensor T to every n+1 simplex. The tensor T is a tensor with these variables of these degrees of freedoms. And when they are fixed, it's a complex number, okay? And then we obtain the partition function or this number Zm by contracting these tensors. So in the tensor level, it is equivalent to contracting. On the manifold level, it corresponds to gluing. So it's basically a functor. This tensor network framework, or this TQFT that I'm describing now, as it has been described in the previous talks, it is a functor from the category of Bordisms to category vect. So it becomes a TQFT when this tensor T is such that this number that we calculate is invariant under retriangulations, because retriangulating a manifold does not change the manifold, the topological properties of the manifold. It's the same manifold topologically. So that number should be invariant under the retriangulations. And you can write on a local condition for this T, which is basically called Pachner moves or Pachner equations. So this tensor T will satisfy equations that is implied by Pachner moves that we will go through. Okay, to make it more visual, a 0 simplex is a point, a 1 simplex is a line, 2 simplex is a triangle, and it goes like that. So in 1 plus 1D, when we glue two triangles like this on the tensor level, it corresponds to contracting this degree of freedom K with contracting degree of freedom K with degree of freedom L, which means that you make this K equals to L and you sum over that K. That is what it corresponds to on the tensor level. The triangulation invariance means that if I triangulate this square in this way or in this way, it should not matter in terms of this tensor contraction, which means that contracting this T tensor along the edge M, which is this equation, should be the same as contracting these two tensors, in this way along the edge N, which is given by this expression. These two have to be equivalent. So this is what retriangulation invariance means. This is called, from left to right, we are doing a 2 to 2 Pachner move. And here there's a 3 to 1 Pachner move, and you can write it in terms of contraction of tensors as well. So tensor T, if you want to construct a TQFT, it has to satisfy these equations. Okay, so let's go over again what TQFTs do. And n+1 state-sum TQFT uses this local data, big T, uses this local tensor T to assign a number to a closed n+1 manifold. Because here everything is contracted, right? So if everything is contracted in this tensor network, it's a number. It assigns a vector V to an n+1 manifold with a boundary n manifold n, which is again closed. So it assigns vector here. And in the tensor network picture, this is basically like everything in the bulk in this manifold Mn+1, all these degrees of freedoms are contracted, but there are non-contracted indices that is supported on this manifold, on the triangulation of this manifold N. So this gives us a vector, and it assigns a projector to this Bordism that maps, that goes from the n-dimensional manifold N to N, big N to big N. Retriangulation invariance means that, if you glue these two manifolds, and on the tensor network level, this is basically multiplying this linear operator with this linear operator. I can just retriangulate the bulk and make it the same as one of these steps. So that gives us a projector. Which basically, to closed n manifolds, this TQFT assigns a linear map. I guess that's what it was in the talks that was on Friday. Okay, tensor network for TQFTs. Now we will show that using this data that is provided us by the state-sum TQFTs, we can actually construct Hamiltonians. And this Hamiltonian is given by this operation that we call lifting. And everything I'm going to do in this slide and some of the next slides is for 1+1 dimensional systems, but it easily generalizes to higher dimensions, like straightforwardly. So this Hamiltonian operator is given by this lifting operation. What you should understand by this notation is that you have two tensors here, a tensor T and a tensor T here. And this Hamiltonian is a linear map when, with inputs I and j and outputs I prime and j prime, and it's contracted along the edge S. Okay. So you can show that multiplying this Hamiltonian by itself, HV square at every vertex V, by retriangulation invariance, it is equivalent to having HV. So all these local terms in the Hamiltonian, in the Hamiltonian that we define in this way, it is a projector simply because of retriangulation invariance. And furthermore, every local Hamiltonian term commute with each other, again due to retriangulation invariance. Let's prove that. So acting first Hamiltonian on the vertex V, meaning that we should lift this vertex, and then HV prime, we lift this vertex. This is equal to first lifting V prime, vertex V prime by Hamiltonian term HV prime, and then by HV, simply because of retriangulation invariance again. What I do is that I retriangulate, instead of this edge, I use the other diagonal, and this equation is implied by retriangulation invariance. And furthermore, using retriangulation invariance, we again show that the cylinder map is a projector, and we define the ground state space, or we can show that the ground state of this Hamiltonian H is nothing but the image of the cylinder map. So take your favorite product state. If it ever has an overlap with the ground state, then this map will project you into the ground state subspace. And the main message here is that all of this is nothing but a tensor network state. And we can go to this picture that we are familiar with by simply going to the dual triangulation here. We just go to the dual, the Poincare dual of this object, and we obtain our tensor network state. So this local tensor A is nothing but this piece here, where this blue degree of freedom is this blue degree of freedom. This black and this black degree of freedom are these black degree of freedoms, and everything else is contracted and is inside of A. By again retriangulation invariance, you can switch back and forth between finite and coarser lattices. So you can, in principle, take thermodynamic limit by going to finer and finer lattices. And here, basically, it constructs an isomorphism between lattices of different sides. Going from the ground state space on this manifold, which is like a bigger in principle from this manifold. Bigger in the sense that it has more triangles in it. By retriangulation invariance, this operation, going from finer to coarser lattice and then coming back to finer lattice, it is equal to the cylinder map and vice versa. So this constructs an isomorphism between, the ground states on the coarser and the finer lattices, which is related to this renormalization tensor network that I showed. So here, this basically implies that given these tensors that satisfy Pachner equations, which gives us retriangulation invariance, we can show that there are equivalences between different lattice sites. So these are actually RG fixed points. Okay, I think I'm going to skip this part because I already exceeded my time by almost 9 minutes. But let me just give the idea that there is in principle a more general framework that studies topological order using tensor networks. And that is basically carrying everything to the virtual level. So we have these local tensors, and we try to come up with line operators or surface operators that are deformable through the tensor network, which we call pulling through. And there's some other condition called TNO injectivity that I'm not going to introduce, but using these two conditions, which a priori is more general than what you would find in a TQFT, you can define a Hamiltonian system, which has potentially ground state degeneracy on different manifolds if you put your system on different manifolds. And these are the only ground states. And this Hamiltonian that you define using tensor networks are gapped, as we described in the beginning of the slides. Okay, so how do we show that state-sum TQFTs are a subset of this framework? Well, if you choose your A's and T's by this data tensor T of the TQFT, these conditions basically imply that these are nothing but retriangulation invariants. And in this 2 + 1D case, this equation and this equation is nothing but a 2 to 3 Pachner equation. You can, as I said, this generalizes to higher dimensions, and in one higher dimension, in 3 + 1 dimensions. This equation is 2 to 4 Pachner equation. And well, in particular, this equation is 2 to 4 Pachner equation. And you can look at other tensor deformation, deforming this and another tensor contracted here on the virtual level, passing through, being pulled through the local tensor. That's going to correspond to 3 to 3 Pachner equation. Okay, I'm going to skip examples, but examples are basically, all of these examples is that you give me a specific local tensor T, and I express all this T in such a way that I find these local tensors A and then these tensor network operator T in such a way that these equations are satisfied. So it's nothing really more than that. It is a cumbersome work, but it kind of follows through if you follow the procedures. So we can explain Dijkgraaf-Witten models, Levin-Man models in terms of tensor networks. This is the local tensor. This is the MPO. This is the pulling through equation. We can also do it in 3 + 1D. Things are in one higher dimension. You can show that they are nothing but the Pachner equations. Okay, so you can tell me, all this is great, right? You expressed everything in terms of tensor networks, but why is this good for me if I cannot find new models? That is in fact a great question. Well, we still don't really know, but here there are two suggestions. A crude way, you just solve the equations, right? You just solve these retriangulation invariance equations, which is provided by Pachner equations. There are finitely many of those. Complicated nonlinear equations, but there are finitely many of them. You assign degrees of freedoms to all these lower dimensional simplices, and you get this tensor T. You know what equations that you have to satisfy for retriangulation invariance, and you try to solve them. If you solve them, you give them to me or to this framework that you listened in this talk. You can write down a local Hamiltonian. You can find its ground states. You can find the operators that maps these ground states to each other. And yeah, you have a topological ordered model. And a more systematic way, which I think is what has been shown in the talk by Niels, you can come up with an N category. So you have your objects, 1 morphisms, 2 morphisms, and up to N morphisms. These are like simple labels in my mind or in this framework. And then you find an associator at the level N + 1. And that tensor T, that associator, you put it in the N + 1 simplex in the tensor network, and you put all these objects to these simplices from 0 to n simplex. Object goes to 0 simplex, the morphisms, k morphisms go to k simplices. If you construct this consistently, this T automatically satisfies Pachner equations. So you get your things automatically. But as we saw in his talk, it may also be challenging to find these structures. And then you can ask me, well, I can do everything that you say with TQFT. So why do I need tensor networks for these? Well, you may need them because tensor networks in principle capture the physics or models away from the fixed points. So here you have your TQFTs and you deform your local tensors. And in principle, you go to different Hamiltonian models that may or may not be in the same phase. And we studied this problem and we found that you need to be clever to do that. So you need to pick your tensor perturbations. Remember, these are not perturbing Hamiltonians. We are really perturbing the local tensor. And in some local perturbations, in some tensor perturbations, you go out of the phase. So this is unstable. But if you pick them in the right way, as in if you respect those pulling through equation and this injectivity equation that I showed, you actually stay in the same theory. We did this for 2 plus 1D, and in principle, it should work for 3 plus 1D as well, but that has to be studied. And this is important and useful for for numerical applications and to study topological phase transitions. Okay, so what are the open problems? Well, finding new models obviously is an open problem. And we did not study unitary gates. This was all about the ground states and the Hamiltonian. And I believe the defect QFTs that has been mentioned in the talk by Niels, that is really about excitations. You poke holes in your manifold, and you could in principle also poke a torus that would give like string-like excitations. And you try to understand the dynamics of this, like what happens when you braid them, what happens when you fuse them. This is widely not studied in 3 plus 1D. It has been studied for some models, but the general formalism is not understood. You can use tensor networks to study topological phase transitions, but you need to be careful about how you are perturbing your local tensor. There's a recent work that studies the error correction properties using tensor networks, but only for one specific model, which is an important one. But this should also be studied, and I think our formalism gives a nice way to do that. And also, when we first saw at the beginning, this topological order does not fit in this local order parameter paradigm, well, it seems like it can actually be extended to something called higher form symmetries. So all these topological ordered systems, or at least some of them, could be understood by, instead of like zero form global symmetry, which is what we are used to higher form symmetries. And this is a work by Seiberg, Kapustin, Gayotto, and Brian Willett. And this is also widely unexplored. And hopefully this framework will help at some point, but a lot of things should be done before that. Okay, thanks a lot for listening, and I'm really sorry for taking this much time. Hopefully we will have 5 to 10 minutes to take some questions. Thanks a lot.
Okay, thank you, Burak, for this nice talk. So we can have some questions. Are there anyone who has the questions, who likes to ask a question? Okay. If there are not any question, I want to ask a question about this TQFT sums. Are there any counterpart for the continuous tensor networks in this TQFT sums? I'm considering it.
Yes, no.
No?
So this is, you know, two things. The answer is no. And there are probably two reasons why that's no. The first thing is that the continuous tensor networks has not been understood that well. And even for the matrix product states, right? There's an MPS called CMPS, continuous matrix product state. So all these things that I mentioned at the beginning, such as this, like given a local tensor, if you satisfy some certain conditions, you know that you get a Hamiltonian H, a parent Hamiltonian, such that besides the ground state.
Okay.
This very fundamental thing is actually not known for the continuous MPS. So that's the first thing. The second thing is that, you know, one may simply forget about this. One may simply say that, well, we just want to have some topological ordered states, and I don't care whether it's a ground state of a Hamiltonian or not. And that's completely fine. Then you may want to mimic the following formalism, where in a continuous tensor network state, you want to have operators on the virtual level that can be deformed through your network.
Okay.
And it is unclear to me how to do that in the continuum case. What we can do is that you try to gradually arrive at the continuum.
Like a taking a limit?
Yes, and in TQFTs we can do that, right? Thanks to the fact that we can just insert triangles, finer and finer triangles. But it is a little different than what people try to achieve by continuous tensor network states. They really try to understand quantum field theories in the most general sense. And in that case, they actually make this local tensor A cutoff dependent, as in lattice spacing dependent. So this local tensor A actually changes when you go from a lattice spacing A to lattice spacing A half. In TQFTs, note that this does not happen. This local tensor A is the same as at every lattice spacing. That is basically the local data that you give me. So that part is the challenging part in my mind. How to come up with a formalism of tensor network states such that the local tensor A is cutoff dependent, lattice spacing dependent. These tensor network operators will also be like that for topological order. And how can we satisfy these conditions in such a way that when these tensors are scale dependent? Yeah, that's a great question. I mean, one should try to do that, you know. I'm sure there are a lot of interesting things there.
Yeah. There is some research on this progress, but as you said, it's not finished yet.
I would say no one even really sat down and tried to do it. Yeah,
maybe this is one of those open questions.
Yeah. That's definitely an open question that I did not actually pose, you know. Yeah.
Okay, we can have some more questions. Are there anyone who wants to ask?
I have a quick one. Are you familiar with COMSOL and like constructing like quantum rings using that type of multiphysics software?
I cannot hear you clearly. Could you repeat? I'm sorry that I'm making you repeat again.
That's okay. I was just asking if you knew of any other. He's put one up there, but I just wanted to share this too. I've used COMSOL with some professors I've worked with before to construct double concentric quantum rings using Schrodinger's equation and different eigenvalues and eigenvectors to change the geometries. I was just wondering if you know of any other programs. He put one up there. I'm going to study that on GitHub. That's nice too. I love GitHub. I was just wondering if you had any other programs or anything that you would recommend looking into as someone researching in the field.
Likely not. I still did not get the problem that you want to apply this framework to. But let me actually give a recent reference which summarizes the tensor networks, and I would say all the important milestones in the past, say 15 years. Not the RG tensor networks, but the ones that I talked about. So it's a recent paper. It's a review paper by Ignacio Sirac, David Perez Garcia, Norbert Schuch, and Frank Verstraete. And the title is Matrix Product States and Projected Entangled Pair States, Concepts, Symmetries, and Theorems. The archive number is QuantPH 2011.12127. So that's a great review by the experts that I actually recommend to everyone.
Actually, we can, if you send this archive number to me, I can who attended the conference.
Yeah, yeah, definitely. I'll do that. Yeah. I'm not sure, Jacob, that will be useful for your problem.
Okay. And my question was just more about more resources that you recommend for learning more basically about quantum computing and everything. That was basically just kind of like a broader statement question.
I see. Uh-huh.
But that right there, that helps, I mean, as well. Thank you.
Yeah. Yeah, why don't we do that offline? I can send you an email.
Okay, yes, sir. Absolutely. Do you want me to put my email in the chat or something? Or?
Yeah, that would be nice. Yeah.
Okay, yes, sir. Thank you.
Okay, great.
Okay, any other questions? I think there is no question, and this concludes our last talk. Thank you again, Burak, for this nice talk. And okay, I think all the talks are finished, and yeah. Okay, thank you everyone for your attendance to the conference. I would like to thank all the audience and all my friends in the organization committee. And we would like to see you in next year's event without COVID, and we hope to see you offline instead of this online conference. And we will send the YouTube information for these videos, also the other references and the other things, and the poll results included. If any of my friends wants to say anything about this conference, you are welcome. And
thank you a lot for joining us.
Thank you all of you for your great speeches and your great attendance. And again, we hope to see you next year. Okay. Okay. See you all.
Thank you everyone for joining us.
Did he just say bereket versin? Thanks, Todor.
Thank you, Todor.
Very nice. Thank you. Thank you.
Thank you, Harold. Thank you, Burak, for giving.
I have a suggestion
really nice
also to put maybe the slides, not only the videos, because sometimes slides are very useful.
Yeah, that will be great and asked actually. So if you can send us your slides, we can put them on the website.
Good.
We will send you an email about these slides, and we will ask a couple of feedback questions to both our speakers and audience.
Exactly. All of your ideas or like suggestions will be highly appreciated for the following year's meetings, so and so forth. And again, thank you all for coming and contributing to this event. It means a lot to us.
Thank you to all the organizers for the great job.
Yeah, thanks.
Thank you.
Thank you.
Have a nice day, everyone.
Goodbye.
Shewao, Jem, Keremcan, and no others that
Bye-bye, Todor.